Okay, let's start. Zishan.
Yeah, hello everybody. This is our project 10 Commandments. We are going to show how we are going to derive quantum mechanics and no-go theorems from fundamental probability.
Yes.
Next slide.
So let us start with the introduction first. So what we shall cover in this first portion of our presentation is basically the formulation of quantum mechanics, its implications, no-go theorems, a proof sketch of a generalized no-go theorem, and inferences from that. So regarding the formulation of quantum mechanics, we shall not delve into the historical path in which quantum mechanics was originally developed, but rather we will take a mathematical approach considering quantum theory to be an extension of classical probability. How is it similar to classical probability? Well, in classical probability, we have vectors that represent outcomes of any given event, and where L1 norm is preserved. But in quantum mechanics, we shall consider the preservation of L2 norm along with the continuity axiom and the idea of measurement. Now, as I stated earlier, the state of a system will encode the probability of outcomes in a vector as given here, and the L2 norm is preserved such that these amplitudes which make up the state of the system, their squares, the sum of their squares will always yield a unit value, that is 1. Yeah. Moreover, there will always exist continuous reversible transformation between any two pure states, and measurement would result in collapse of the state, whose outcome will be governed by the probability distribution of the state itself. Now, let us first of all look into the fact like what does preservation of norm signify? Well, in classical probability, where we preserved L1 norm, all transformations could be represented as stochastic matrices. Similarly, in the case of quantum mechanics, it will be represented by unitary matrices. Now, one might always ask, what about other norms, like other than L1 and L2? Why can't we have any arbitrary LP norm? Well, if we have any arbitrary LP norm where we have non-trivial transformation that does not involve just reshuffling of elements of our given state vector, then we find that P must either be 1 or 2. Also, based on these axioms, we can also develop statements that govern the system of composite systems, which involve degrees of freedom of the system and dimension of the system. More specifically, we can get a relation between subsystems and their composite systems with respect to the above two entities. Okay, so based on this formulation, what can we imply? Well, first of all, obviously, we can imply linearity and unitarity, which are the two basic constants, and which should always be respected and shall not be contradicted throughout any implication that we might get out of quantum theory. Also, several of the idiosyncrasies of quantum mechanics can be explained. For example, why do we use complex numbers rather than real numbers? Well, this is basically an extension of the axiom of continuity, as a result of which we are required to operate on an algebraically closed field. Thus, instead of real numbers, we need to consider complex numbers. Moreover, as we stated earlier, all operators must be unitary. As a result, quantum computing also requires to be reversible. Now, why should all transformations be linear? Well, as stated by the axioms, linearity is quite implied. But if we think about it and like move out of our given formulation here, we can also make two major arguments regarding linearity. The first one was made by Wigner and Bergman and involved invariance of inner products and basically their absolute values. And even if we consider this not to be strong enough, for example, there do exist non-linear formulations of quantum mechanics, we can also come up with something stronger, which effectively is also based on computational complexity, which states that if quantum mechanics were non-linear, then one could always build a computer to solve NP-complete problems in polynomial time. So now that we have covered the implications, let us move on to no-go theorems. Zisha?
Yeah. So based on the two limitations on our transformations, that is unitary and linearity, we create no-go theorems which restrict the transformations. So the general statement for a no-go theorem is given an arbitrary state psi and a blank state. You cannot create a transformation which transforms psi and a blank state into psi and a function of psi. Next slide. So how do we prove it? Every function can be expressed as a matrix given that it's linear. So we can split them into cases where K is unitary, K is anti-unitary, and K is a combination of unitary and anti-unitary, a linear combination which still preserves now. Next slide. So for the case of unitary, we just multiply, without loss of generality, we can assume psi to be alpha 0 plus beta 1. Further, we apply unitary operation on psi individually on 0 and 1 since u is linear. We can see that we obtain two different equations or two different right hand sides when applied in different ways, and they are only equal if either of them are 0. Since the sum has to be 1, this means that the only case where it is applicable or general is when alpha equal to 1 or beta equal to 1, that is no superposition. The same thing can be applied for anti-unitary. We obtain the same result. Next slide. Further, these two, the same operation or the same procedure can be applied for linear combination of both. It's just that the equations will be different. This results into something big, but the math works out. Next slide. So what do we do after this? So we can see that this generalization can be used for further corollaries, even though this generalization did not come before its corollaries. If a function is f of x equal to x, then it is no cloning. If f of x equal to x bar, then it's no anti-cloning. And you can reverse no cloning to obtain no deletion theory. Moving on to no cloning.
Okay, so here we shall first deal with the first example of a no-go theorem, and so why are we interested in no cloning? Well, before that, let us give you a brief background. For example, consider two people, Shreyas and Kumar in this case, such that they are light years apart and they have entangled qubits. They do possess a pair of entangled qubits. Now, what Shreyas and Kumar want to do is that they want to transmit information instantaneously, like at a speed faster than light. So basically, when Shreyas measures his own qubit, Kumar also wants to know what he has measured and what he has obtained. Now, does that mean they can communicate at a speed faster than light? Well, no. The reason is that Kumar is still unable to tell in which basis Shreyas measures his qubit. So, is there any way that Kumar can find this out? Well, there is a way, and that involves Kumar copying his qubit unlimited number of times. However, is this truly possible? Well, no. And more importantly, we can prove it. We can prove that there exists no possible method by which we can create an independent as well as identical copy of any arbitrary quantum system, and that is what we call as no cloning theorem. Now, formally, what is the theorem statement? Well, we basically deal with an unitary operator. We basically say that there exists no unitary operator U over a Hilbert space that involves a system of two qubits, such that when we apply unitary over the operator over the entire system, we get copies of the two copies of this original normalized state. Now, let us consider the proof. Let us think about how we can prove this. Well, let us prove this by contradiction and assume that certain transformation exists. Well, in that case, we shall, given that psi is equal to alpha 0 plus beta 1, we shall have the following result, and as a result we shall obtain this such that upon unitary transformation over this vector, we get alpha square, alpha beta, and beta square. Now, this is certainly not possible. Well, why? Because this unitary transformation U has to be a linear transformation, and there cannot and it cannot result in quadratic terms, and thus it is not an unitary transformation. As a result, we derive at the contradiction, which proves that no cloning is not possible. There we can also express this in a different way. Zishan, would you want to elaborate on the proof?
So continuing from no-go theorem, instead of using f of x or f of psi, we just use psi. So next slide. So we apply unitary transformation on the complete system first, which results in the first equation. But in the second part, we first take the tensor product and then apply unitary transformation on the individual parts, that is u00 and u10. This again gives us two equations which have to be equivalent because we just change the form. But we can see that, next slide, this is only the case when either alpha or beta is 0, since the middle two terms have to become 0, which means that this again implies that it is only possible for certain states, that is 0 and 1.
Yeah, so moreover, we can also prove that we can also have a different proof that approaches the problem in the following way. Suppose you have two arbitrary quantum states V and W, and you apply unitary over V and normalized ancillary qubit and obtain VV, and similarly you apply the same thing on W. And now, since we know that unitary transformations are inner product preserving, we shall obtain the following, which basically states that the inner product of V and W must be equal to the inner product of V and W whole squared. As a result, this implies that a unitary can perfectly copy if and only if the two vectors V and W belong to the same orthonormal basis, because of this inference that we get from the above deduction. As a result, we can safely say that no universal unitary matrix U can clone a general quantum state. Thus, we successfully have proved no cloning theorem. As a conclusion, Zishan, would you like to take
this means that we cannot use classical error corrections for quantum error corrections since we cannot clone.
Yeah, and moreover, we cannot distinguish between quantum states. Also, there are several no-go theorems such as no deleting and no teleportation, which can be implied, which can be implied based on no cloning theorem. Also, it validates no communication theorem and holds for black hole complementarity. However, we should also say that this does not mean that the fact that perfect cloning is impossible does not mean that imperfect cloning is not at all possible. In fact, it is actually possible, and there has been many approaches towards probabilistic cloning and so on. And so that is where we would like to end our presentation. Thank you.
Thank you.